Okay, everyone. My name is Shin. I'm the author with the underscore on the slides. And today I'm going to discuss the factors that we think drives liquidity across different decentralized exchanges. Well, specifically here, I'm just using a sample of Uniswap protocol, but you'd expect that LPs behave sort of consistently across different DEXs because nothing stops them from being on a different one. And this is joint work. I'm at Uniswap Labs, and this joint work with Columbia University and Circle. Yeah, my opinions only and not that of my employer. So the role of liquidity is, as everyone understands, to be very important, but there is always this perception that maybe liquidity in DEXs behave a bit differently than liquidity elsewhere. And it's unclear, first, whether that's true, and second, if it's true, what explains it? Because you can say, oh, it's a different group of people who's providing liquidity, or you can say, regulatorily they have different constraints, or they require different type of return, or they just, think differently, build differently. So the goal here is to not make a normative statement. So I'm not here to say whether people are doing the correct thing or the optimal thing. I'm also not here to predict what happens in the future. I'm simply here to take what happened in the past and try to explain it and say, these things happened, and I think it's statistically correlated with these other factors. Maybe some of them are causal, some of them are not, but that's sort of the goal of the study. So the first question to ask is, what are the key on-chain, off-chain factors that drive liquidity on DEXs? And when I say drive, I mean that a change in that factor today would likely lead to some predicted change in the future, in future liquidity on the DEXs. So some of the examples are gas prices, token pair returns, volatility, the amount of fee you can earn in the pool, and the sharpness of your counterparty. Now, once you identify the factors, the second question you can ask is, how do these factors affect liquidity? So specifically, you can mechanically break down liquidity into TVL and concentration, and I can show you how we do it. And we can try to ask which of these are most affected by these factors that we identify. So the TLDR here is gas prices and returns mostly affect liquidity concentration. Volatility, the amount of fee you earn, and the sharpness of your counterparty act through both channels. And the final question is, how does external liquidity from other DEXs or liquidity that is not public affect on-chain liquidity? And we found that competitor share, which is defined to be the amount of liquidity in other DEXs, to negatively affect liquidity through the channel of concentration, and internalization by aggregators, meaning if an aggregator chooses to take the trading flow in their own book or send it to some liquidity sources outside of Uniswap, that actually has no statistically significant impact on market depth. So this is just summarizing what I have just said. The first thing is we should think about liquidity as TVL plus concentration. Second thing is we identify volatility, fees, and informed trading to affect the total depth of liquidity. And then competition between DEXs creates liquidity fragmentation. Finally, aggregators don't necessarily kill DEXs. They can coexist. Okay, I'm skipping the literature review because I used this for academic presentation before. I'm also skipping Uniswap intro because I would assume people know it. This is just to show what concentration looks like. Okay, so this is the data source. We used data from Uniswap v3 going from May of 2021 to July of 2024. So that's about 3 years of data. And we had all of these pools in our data sample. So across 4 different chains, in each one across 7 different pools, 7 different pairs. And some of these pairs have different fee tiers. Now, let's talk about the outcome metric. So in a simple setting, you can think of our analysis as a regression. And in a regression, you have a y, and you have a bunch of x's. So this effective spread is one of the y's. And what do I mean by it? I mean that if you simply take a fixed amount of ETH and you try to simulate a transaction in a liquidity pool, the amount of price movement that your trade would incur, or rather, sorry, it's basically the same thing, but the difference between the quoted price and the quoted price for a sell versus a buy of the same fixed amount gives you this spread. And we get this quoted price through a quota contract. The second y, and again, we're not touching the x's yet. The second y in the regression is TVL, and that's pretty obvious. So we'll run 2 regressions, one with the first y, one with the second y. And here I'm just showing what the y's look like as a time series. So on the left side, you have 4 chains of 1 pool. And keep in mind that we have a ton of pools, and this is just for 1 pool. And you can observe the change in spread on the left side with log scale, and the TVL on the right side with log scale as well. And this is taking sort of the same data from before, and instead of treating it as a time series, I'm just showing it as a histogram to give you an idea of the distribution. And you can see that for the same fixed size trade, the liquidity on mainnet is much deeper. And so there's an inverse relationship between spread and depth. The deeper the liquidity, the smaller the spread for a fixed size trade. And here you can see that for the fixed size, the spread on mainnet is much smaller, meaning the liquidity on mainnet is much deeper. Okay, so those are the 2 x's, the 2 y's. And remember that when we set out, we said the first goal is to identify the factors that drives liquidity. The second goal is to understand how those factors drive liquidity. So here I'm going to introduce some intermediate y's. So you can think of them as y's that we suspect are representative of the channels through which our factors affect the final y. One of them is this thing we call a counterfactual V2 spread. So what this is you take a V3 pool and you look at the TVL in the pool. You say, okay, let me withdraw imaginarily, not in reality. Imaginarily, you withdraw all the assets in the pool and you rebalance it such that it's the same pair, but it's a V2 pool. You create this imaginary new pool and you simulate the same fixed size transaction in this new pool. What this does is it isolates the effect of TVL in that V3 pool, and the difference tells you how concentrated your V3 pool is compared to an imaginary V2 pool of the same TVL. So let's just take one pool as example. Let's say we have a V3 pool that's extremely concentrated. What that means is for a size that's within the TVL of that pool, it's not going to create any price impact. Or if you compute that first Y, which is spread, you will see its spread is tiny. But if you create this imaginary V2 pool and simulate the same transaction, it will have a bigger spread. And the difference between the two tells you that the depth in that V3 pool is mostly coming from concentration instead of TVL, because the same TVL on the V2 pool would do much worse. And now, just to formalize it, we're going to define this quotient to be the ratio of the actual V3 pool spread versus the spread we compute on this imaginary V2 pool. And this tells us, as I just kind of walked through an example, how well concentrated this V3 pool is. Okay, so here's an example of a well concentrated pool, which is WBTC 30 bips pool on Polygon. And you can see that the V3 spread consistently stays under the imaginary V2 counterfactual spread. And now here's an example of what we call a poorly concentrated pool, because a lot of the times concentration gives you no additional benefit in terms of depth. You can do equally as well by just putting that money in a V2 pool. Okay, so now I just defined, 3 Ys. The first two are spread and, well, I forgot the notation, but you kind of remember there are 3 Ys. And I'm going to regress them on all the factors that I think is going to affect LP's behavior. Specifically, their gas prices, return on the pair of the past. So notice that there is a subscript T+1 for all the Ys, and there is a subscript T for all the X's. So I'm looking at the correlation between future liquidity depth and current factor values. So gas price, log returns, volatility, fee revenue, markout. And there's some statistical control that I'm adding to the regression. Okay. After we do those 3 analyses, we also want to say, is our result robust against some slight changes in experiment design? So we're going to kind of change the trade size, change the horizon, and change the horizon of 2 of the factors. Okay, so now I'm going to overwhelm you with a very big table. Just be mentally prepared. But before I show you the number, the horizontally is what we have defined to be the Ys, so the outcome metrics that we're interested in explaining, and vertically are the factors. So let's look at the first one. The first Y is just the V3 spread. And this shows that, in fact, log prices of this period has no statistically significant impact on depth in the next period, but return does. And negative is good, or sorry, negative is intuitive, because if you have a high return this period, there will be more liquidity in the next period, which means less spread. So that's kind of the direction we're going. Similarly, volatility is intuitive because more volatility, less liquidity. Higher revenue, more liquidity. That's easy to understand. And then markout, more markout, meaning you make more statistically from your counterparty, more liquidity. So now I'm going to try to break this down, right? The V3 is sort of the combined outcome, And now I'm showing the counterfactual V2 spread, which is the effect of TVL, and the spread quotient, which is the effect of concentration. So the first column should be the combined effect of the second and third column. And now it's a little interesting because you can see that gas prices actually has a significant effect. And it affects concentration. When gas price is high in this period, concentration will reduce in the next period significantly. And then for return, it's also working mostly on concentration. And sometimes you can think of concentration as active liquidity is pulling out, and passive liquidity is staying in the pool. Volatility and fee revenue, on the other hand, affects both channels in the same direction. Markout, a little bit unintuitive here, but markout has a weird effect on this quotient, or maybe concentration. And let's just think about this for a minute. Markout is the sharpness of your counterparty, and you would expect, markout is like the inverse of that because the sign is reversed. But if you would expect that the smarter your counterparty is, the higher the selection effect is for liquidity in the pool, and you would expect liquidity to be maybe more concentrated. But what this shows is actually the opposite, that when the traders or the takers of liquidity in the pool is smart, the active liquidity kind of leaves the pool, and we're left with a pool with relatively less concentration, which I guess also makes sense, but it's just kind of interesting that it's going in two directions. Okay, and I'm gonna skip because of time. This paper is online, so if you're interested in any specific number, you can just go online and search for this paper, what drives liquidity. And then quickly want to mention two other things we look at. One is the market share of competitors, and the second is the internalization ratio. And both of them, we do it through kind of a similar setup, except we just add those two factors into the regression. And okay, maybe one thing to highlight is we show that at least for the final outcome that we're interested in, there's no statistically significant number for this factor, which means even if you have the likes of 1inch and CalSwap, where they take trader order flow first, and they try to internalize it or send it to people who has the ability to internalize it before it's sent to DEXs, the existence or the prevalence of those players didn't statistically affect the depth of liquidity on chain. But again, I just want to remind you that this is an empirical study, so it doesn't say what should happen or what is optimal. It simply describes what has happened, and this is what we observed so far. Okay, so quickly summarize. Liquidity, we think of it as a combination of TVL and concentration. And then we identify the key drivers to be gas prices, liquidity, volatility, return, fee revenue, and markout. The last three are kind of different ways of expressing the same thing. And then there are two channels that we test all these factors through, and we found that some subset affect specific channels uniquely. Finally, we tested external liquidity and their effects on liquidity within Uniswap protocol, and we found that competition intuitively reduces concentration within Uniswap, and internalization so far does not harm overall market depth. That is it. If you want the paper, you can scan. Thanks. Do I have time or? Oh, just on time. Okay, so if you want to ask me, I'm going to be outside.